Hey everyone, it's Emma AI, and welcome to another episode of our cybersecurity journey. Today we're diving deep into a critical aspect of network security, Layer 3 attacks and how we can fortify our defenses against them. Grab your coffee or your favorite energy drink because this dive is not just deep, it's extensive. I promise, by the end of this video, you'll have a new appreciation for the complexities of network routing and security. We'll explore how these attacks happen, why they're so dangerous, and what you can do to protect your networks. Let's start with the basics, routing protocols. Picture the internet as a vast, complex road network. Routing protocols are your GPS, ensuring that every packet of data finds its way from point A to B. They're constantly learning the layout of this network, choosing paths that offer the best service. Think of it as finding the highway with the least traffic and the shortest distance. But it's not just about finding any path, it's about finding the best one. Imagine if every time you needed to go somewhere, your GPS had to decide the optimal route based on traffic, road conditions, construction zones, weather forecasts, road maintenance schedules, emergency rerouting due to accidents, and even seasonal changes affecting travel. Routing protocols are designed to handle two main tasks. They learn about the network topology, including all possible paths to destinations, and they choose the optimal route based on criteria like bandwidth, latency, cost of transmission, security policies, and even user-defined preferences. They're also smart enough to automatically reroute traffic if there's an outage or congestion, much like a detour sign when there's construction on your usual path. Think about the last time you were driving and had to take a detour. Routing protocols do this for data, ensuring it gets where it needs to go, even if the original path is blocked. But what happens when these protocols, which are essentially the navigators of our digital highways, are manipulated or tricked into leading data astray? There are two types of routing protocols we need to know about: interior gateway protocols, IGPs, and exterior gateway protocols, EGPs. IGPs are like local traffic cops, managing how data moves within a single network or organization. Examples include OSPF, which stands for Open Shortest Path First, EIGRP, Enhanced Interior Gateway Routing Protocol, and ISIS, Intermediate System to Intermediate System. These protocols ensure that your data travels efficiently within your network, adapting to changes or issues in real time. They're crucial for maintaining a smooth flow of information inside your network's boundaries, making sure every packet of data finds its way home, no matter the obstacles or new network developments. Let's dive deeper into these. For IGPs like OSPF, it's all about having a detailed map of the network where every router shares its view with others. OSPF uses a link state routing algorithm, which means each router builds a comprehensive map or link state database of the network. This allows OSPF to compute the shortest path to any destination within the network, much like having real-time traffic updates for every street in a city. It's not just about speed, it's about ensuring data integrity and efficiency by maintaining an up-to-date network-wide view, which is essential for quick adaptation to network changes. EIGRP adds another layer of sophistication. It doesn't just look for the shortest path, it considers the quality of the path, including bandwidth, delay, reliability, load, cost of the link, and even historical data usage patterns. EIGRP employs the diffusing update algorithm, DUAL, which ensures that if one path fails, there's already a calculated backup path ready to take over, much like having an alternate route pre-planned for when a road is closed. This foresight can be the difference between a seamless data journey and a network congestion nightmare, ensuring there's always a plan B or even C. Intermediate system to intermediate system, or ISIS, though it might sound like a relic from the past, is still pivotal in many large networks due to its scalability. It's particularly effective in networks segmented into areas, where each area can manage its own local traffic while still being part of the global network. Imagine if each neighborhood in a city had its own traffic management but could coordinate with others when needed. ISIS offers that level of autonomy and coordination, making it invaluable in large-scale operations where managing vast networks is like orchestrating a symphony of data with precision and efficiency. On the other hand, exterior gateway protocols, or EGPs, deal with routing data across different networks or autonomous systems. BGP, or Border Gateway Protocol, is the most prominent EGP. It's like the ambassador of the internet, facilitating communication and data transfer between different ISPs, ensuring that your Netflix binge doesn't get interrupted by routing mishaps. BGP doesn't just route, it negotiates, ensuring that data can cross international digital borders seamlessly and securely. It's the protocol that keeps the internet interconnected, allowing for the vast digital commerce and communication we enjoy today, but it's also where the most sophisticated attacks can occur. When we talk about BGP, it really stands out because it's not just about routing, it's about diplomacy and policy. BGP allows networks to announce their routes to the world, but it also lets them set policies like preferring one network path over another for political, economic, security reasons, or even environmental considerations. It's like how countries might have trade agreements that influence how goods move between them. BGP can be influenced by everything from business relationships to geopolitical tensions, making it both powerful and potentially vulnerable to manipulation, where one wrong policy can lead to widespread disruption. Now let's shift gears to the darker side, Layer 3 attacks. Imagine you're sending a letter, but someone intercepts it and reads or modifies its content. That's essentially what happens in a machine-in-the-middle attack. Here, attackers use techniques like IPv6 router advertisements to trick devices into thinking the attacker's device is a legitimate part of the network. This allows them to eavesdrop or redirect traffic. It's like someone posing as your postal worker, opening your mail and possibly altering it before it reaches its destination. This breach of trust can lead to data theft, service disruption, or even corporate espionage, turning your secure communication into a playground for hackers. Another type of attack involves unauthorized routing updates. Imagine if someone could claim they control the route to your favorite website, redirecting all your traffic through their network. That's what happens in BGP prefix hijacking. Attackers can make false announcements, leading to traffic being diverted, which can result in data theft or service disruption. It's like claiming ownership of a major road to divert traffic for your own benefit, potentially causing chaos or profit. This can lead to significant downtime or even expose sensitive information to unauthorized parties, affecting not just one user but potentially thousands or millions. Wormhole attacks are a bit more insidious. Here, an attacker who has gained access to one of your routers creates a tunnel through which they can redirect your network traffic. It's like having a secret underground passage that only they know about, allowing them to snoop or tamper with data as it passes through. This isn't just about reading your data, it's about potentially altering or redirecting it to serve the attacker's ends, creating a hidden path where they can manipulate your information flow. These attacks are particularly hard to detect because they can mimic normal network behavior, making them a stealthy threat to network integrity. To combat these threats, understanding mitigation strategies is key. For routing protocols, the cornerstone of security is authentication. Without authentication, any device could pretend to be a legitimate part of your network, leading to chaos. Imagine if anyone could claim they were your trusted courier. You'd have a mess on your hands. Authentication ensures that only authorized routers can send or accept routing information, maintaining the integrity of your network's map, much like a secure badge check at an exclusive event. Plaintext authentication is a no-go. It's like sending your keys through the mail in a clear envelope. Instead, we employ hashed authentication using strong algorithms like HMAC SHA-256, which encrypt the key, making it unreadable to prying eyes. This is akin to sending your keys in a locked box where only the recipient can open it. By using hashing, we ensure that even if the data is intercepted, the key remains secret, protecting the authenticity of routing updates from being compromised. For BGP, which historically has only supported MD5 authentication, we've introduced Resource Public Key Infrastructure, or RPKI. This system works like a digital passport for networks, verifying who can legitimately advertise routes, reducing the risk of hijacking. It's like having a global registry where only authorized entities can claim ownership of a route, much like how countries have sovereignty over their territories. RPKI adds a layer of cryptographic validation, making unauthorized route announcements significantly harder, thus fortifying one of the Internet's most critical protocols against deception. Keychains add another layer of security. Think of them as multiple keys for different rooms in your house, each with its own expiration date. This allows for automatic and regular key rotation, ensuring that if one key is compromised, it's only useful for a limited time. It's like having a dynamic security system where the locks change periodically, keeping intruders guessing. By implementing keychains, you're ensuring that even if a key is stolen, it becomes obsolete quickly, minimizing potential damage by narrowing the window of opportunity for attackers. Setting up these key chains on routers involves specifying when each key is active for sending and receiving data, essentially automating the process of changing your network's locks periodically. This proactive approach to security means that even if someone sneaks a key, it won't be valid for long, minimizing potential damage. It's like having a security system that's always one step ahead of potential thieves, ensuring your network security evolves with the threats. When it comes to wormhole attacks, the strategy is straightforward but strict. Secure your routers. It's like having a high security gate around your property. If intruders can't get in, they can't set up their secret tunnels. This means enforcing strict access controls, regular security audits, and ensuring that remote management is as secure as possible. If your router is Fort Knox, your network traffic remains safe. Ensuring physical security, updating firmware, and securing management interfaces are all part of this defensive strategy, creating a fortress around your network's command center. Detection of these attacks often requires vigilance and the right tools. If you notice that your data is taking an unusually long route, or if there's an unexpected delay in transmission, you might be dealing with a wormhole or a hijack. Tools like HPing can send probes with specific TTL settings, helping you trace the actual path your data takes, much like following breadcrumbs to find where your data might be going off track. Monitoring latency, path lengths, and unexpected network behavior are key to early detection and response, allowing you to spot and mitigate threats before they escalate. Routing protocols are not just about getting data from one place to another, they're about ensuring that this transfer is done with the highest efficiency, security, and reliability. They're like the unsung heroes of the internet, working behind the scenes to make sure your data arrives at its destination as intended. Understanding how they work is fundamental to both using and securing your network, turning what could be a chaotic digital landscape into a well-orchestrated ballet of data movement. For OSPF, the process involves each router broadcasting its link state information to all others in the area. This creates a situation where every router has the same detailed map of the network, allowing for immediate, informed decisions about the best path for data to take. It's like having an up-to-date traffic report for every single route in your city at all times. OSPF's design ensures that if any part of the network changes, all routers know about it almost instantly, allowing for dynamic rerouting, which is crucial for maintaining network resilience. EIGRP goes a step further by not only considering the shortest path, but also the quality of that path. It uses metrics like bandwidth, delay, reliability, load, MTU, and even historical traffic data to decide the best route. Imagine if your GPS could not only tell you the shortest way, but also which route would give you the smoothest drive based on road quality, current traffic conditions, historical data, and even weather forecasts. EIGRP's adaptive nature means it's always optimizing for the best possible journey for your data, ensuring that even in complex networks, communication remains smooth and efficient. ISIS, with its hierarchical approach, allows for large networks to be segmented into manageable areas while still maintaining connectivity across the entire network. It's particularly useful in environments where network management needs to be decentralized but still coordinated. This is akin to a city where each district manages its own traffic but can collaborate with others for citywide events or emergencies. ISIS's structure allows for efficient scaling while maintaining control, ensuring that even in vast networks, management remains feasible and secure. BGP, however, is where the real international negotiation happens. It's not just about finding the path, it's about choosing paths based on business agreements, security policies, geopolitical considerations, and even environmental impact assessments. BGP lets network operators set complex rules about how their data should be routed, much like countries negotiating trade routes or diplomatic channels. This level of control means BGP can be both a powerful tool for connectivity and a potential point of failure if exploited by attackers, requiring constant vigilance and innovative security measures. Now let's talk about the threats at Layer 3. Machine-in-the-middle attacks are particularly dangerous in IPv6 networks where router advertisements are used for auto-configuration. An attacker can easily pretend to be a legitimate router, leading to data interception or redirection. It's like someone faking a road sign to divert traffic for nefarious purposes. This type of attack can go unnoticed if you're not vigilant, as it leverages the trust inherently built into network communication, turning what should be a secure path into a trap. Unauthorized routing updates, especially through BGP, are like someone claiming they control a major highway. By announcing routes they don't actually manage, attackers can redirect vast amounts of internet traffic through their systems. This could lead to data interception, service denial, or even enabling attacks on other networks. The global nature of BGP means these disruptions can have widespread effects, potentially affecting millions of users, causing not just inconvenience but potentially catastrophic security breaches. Wormhole attacks are about creating hidden paths within your network. An attacker with access to your routers can redirect traffic through these paths where they can inspect, modify, or even replicate data before sending it on. It's like if someone could build a secret tunnel under your city, controlling where your traffic goes. These attacks are especially tricky because they can be masked by normal network operations, making detection a challenge, requiring both sophisticated tools and a proactive security mindset. Mitigation starts with securing how routing information is shared. Authentication ensures that only trusted devices can influence routing decisions. Using plain text for this is as insecure as shouting your secret in a busy marketplace. Hashed authentication, however, is like whispering it in a secure, soundproof room. This ensures that even if someone overhears the conversation, they can't make sense of it without the key, protecting the sanctity of your network's routing decisions. For BGP, RPKI has transformed how we validate route announcements. By providing a mechanism for networks to prove their IP space ownership, RPKI reduces the opportunity for rogue announcements. It's like having a notarized document proving land ownership in the digital realm. This added layer of security means that even if someone tries to make false claims about route ownership, they can be easily disproven, safeguarding one of the internet's foundational protocols. Keychains are an evolution in security where keys are rotated regularly, much like changing the locks on your doors every few months to ensure no one has a permanent key. This rotation is automated on routers, making security maintenance proactive rather than reactive. By changing keys, you're essentially resetting the security handshake, ensuring that even if one key is compromised, the window for misuse is severely limited, keeping your network's security dynamic and robust. Securing routers against unauthorized access is paramount. This involves everything from physical security to ensuring that remote access protocols are as secure as possible. If an attacker can't get into your router, they can't create these secret tunnels or alter your routing tables. This means implementing strong authentication measures like multi-factor authentication for remote access, and ensuring that all management interfaces are only accessible from trusted networks or through VPNs, creating multiple layers of defense. Detection can be tricky but is essential. Tools like HPing allow for network probing to check if your data is taking the expected path or if there's an unauthorized detour. If network performance suddenly drops or routes seem longer, these could be signs of an attack. Network monitoring tools should be set up to alert on unusual patterns or anomalies in traffic flow or path length, providing you the chance to investigate and respond promptly, turning potential threats into opportunities to strengthen your network's defenses. But remember, cybersecurity isn't just about setting up defenses. It's about understanding your network, anticipating threats, and being ready to adapt. It's about building a network that's not just secure but resilient, able to recover from attacks with minimal disruption. This involves regular testing, such as penetration testing, to find and fix vulnerabilities before attackers do, ensuring your network is always one step ahead in the cybersecurity game. Now let's talk a bit more about practical steps you can take to implement these security measures. For those of you who are managing or planning to manage a network, regular updates to your routing protocols are essential. Not just software updates, but also updates in your security policies. This could mean revisiting your authentication methods, ensuring that each router in your network is configured with the latest security patches, and regularly reviewing who has access to these critical devices. Moreover, consider the human element. Training for your team is crucial. Even the best technical defenses can be undermined by human error. So educating your staff on the basics of network security, how to spot suspicious activities, and the importance of following security protocols can be as important as the technical measures themselves. Another practical tip is to engage in community forums or join security groups where you can learn from real-world scenarios. There's a lot of collective knowledge out there about how others have tackled similar issues. This can be a goldmine for learning about new threats or innovative solutions you might not have thought of. Finally, don't forget about the power of simulation. Regularly simulate attacks on your network in a controlled environment. This not only helps in training your team, but also in testing your security measures to see if they hold up against various attack vectors. It's like a fire drill for your network. You're preparing for an emergency you hope never comes, but if it does, you'll be ready. As we wrap up this deep dive into Layer 3 security, I want to leave you with this thought. In the digital world, security is not a destination, it's an ongoing journey. Every day brings new challenges, but also new opportunities to strengthen our defenses. The knowledge you gain today equips you to face tomorrow's threats more confidently. So I ask you again, have you ever faced a Layer 3 attack? What lessons did you learn, and how have you applied them to enhance your network security? Share your stories, your insights, and your questions in the comments. And if you found this video enlightening, please give it a like, subscribe for more cybersecurity content, and don't forget to hit that notification bell so you never miss out on our next adventure into the world of digital security. So keep learning, keep adapting, and remember, in cybersecurity, complacency is your enemy. Stay vigilant, and let's make our networks not just places where data travels, but fortresses where it's safe. Thanks for tuning in, and until next time, keep those networks secure.